Have you ever noticed your favorite fan losing speed during a scorching afternoon, or watched the refrigerator light dim because of one annoying issue? Low voltage. In many homes, this problem shows up almost every day. Sometimes the inverter refuses to run. Other times, the television screen becomes faint, and calling an electrician only adds more expense and frustration. But what if the answer was neither costly nor complicated? What if a simple DIY setup worth 200 rupees could solve the issue right at home? That was the surprising idea. For roughly the cost of a monthly streaming subscription, there appeared to be a way to reduce low-voltage trouble without depending on an electrician. The situation became serious 1 month earlier when a small neighborhood outside town experienced repeated voltage drops every evening between 6 o'clock and 10 o'clock p.m. Dinner time arrived under weak lighting. An 8-year-old nephew struggled to finish homework using a torch. The refrigerator stopped cooling properly, and milk spoiled overnight. Even the washing machine refused to start. Most nearby residents reacted the same way. Some complained constantly. Others contacted the electricity company, only to hear that no repair could happen for weeks. A few families purchased expensive stabilizers, but those units protected only one appliance at a time and cost far more than many households could comfortably spend for every room. Frustration slowly turned into curiosity. During a rainy evening spent reading internet forums, there was a post written by a retired electrical engineer from Kerala. He explained inexpensive low-voltage tricks designed for village schools. The methods were basic but effective, allowing classrooms to keep lights running despite poor power supply. That single discovery changed the feeling of helplessness into hope. The design itself looked simple: a homemade voltage booster built with an ordinary transformer, several wires, and fuse protection. According to the engineer, common electrical parts costing around 200 rupees could create a small boost for household circuits, lifting weak incoming voltage enough to help protect home appliances. The biggest surprise was that no advanced technical skill seemed necessary. There was no need to become an expert or even master soldering work. The process only demanded caution, patience, and respect for electrical safety. The decision was made to test the 200 rupee voltage boosting device personally, either solving the nightly power drops or at least learning something useful in the process. The materials required were all basic hardware shop items: a small 12-volt 5-amp transformer, a blade fuse holder together with a fuse, thick copper wire, a plug top connected to a socket. Every item cost somewhere between 20 and 70 rupees locally. Nothing expensive, nothing unusual. The transformer served as the heart of the setup. Normally used for charging small batteries, it was repurposed to slightly increase the incoming household supply voltage. Naturally, one major concern appeared immediately. Was the arrangement actually safe? Questions about short circuits and damaged appliances became impossible to ignore. Nobody wanted a cheap homemade device destroying an expensive television. Circuit diagrams were reviewed carefully. Information was checked multiple times. An electrician friend was even contacted for advice. The answer remained consistent. If wired correctly and protected properly, the system could operate safely. The fuse worked as the first line of protection, disconnecting power immediately if something failed. Even with that reassurance, plugging the device in for the first time still felt nerve-wracking. Handling 220 volts always carries a sense of danger, as though one mistake could destroy equipment or create something worse. Every connection was checked carefully. The transformer was wired. The fuse installed, plug top secured. Everything was prepared before testing began on the living room lighting circuit. The switch flipped on. There was a moment of tension, waiting for sparks or failure. Instead, everything stayed stable. The ceiling fan immediately spun faster. Nothing failed. After an hour, appliances were operating more efficiently and staying cooler than before. Confidence grew quickly. By the second evening, the kitchen lights remained steady without flickering bulbs, and the 8-year-old nephew finally completed mathematics homework under bright white lighting again. News traveled fast through the neighborhood the following day. One house after another became curious about the homemade circuit. 3 nearby homes eventually tried the same arrangement, and every one of them reported identical results. The most shocking part was not simply that the system worked. It was the fact that it worked at such a low price. When the local electrician inspected the wiring, he smiled and admitted that this type of trick had existed for years among old-school electrical hobbyists. Very few people attempted it themselves, because most assumed any do-it-yourself electrical project must automatically be dangerous or unreliable. Yet the opposite could also be true. Allowing appliances to operate for months under weak voltage can slowly damage motors, fans, compressors, and sensitive electronics over time. Low voltage itself creates long-term stress on household equipment. Still, one important question remained: how could such a cheap and basic setup actually solve a low voltage problem? And were there side effects or limitations people needed to understand before attempting it themselves? The answers required a closer look at how the device functioned and why proper precautions still mattered. How could such a tiny transformer and a few wires handle the same low-voltage problem that forces expensive stabilizers to struggle? The real brilliance of the 200 rupee setup starts here. A transformer is not some mysterious machine that magically converts weak voltage into unlimited power. It operates using the same principle found across the electrical grid itself, only on a much smaller and controlled scale designed for household circuits. When incoming power falls to around 160 or 170 volts, while the normal requirement remains 220 volts, the transformer gently raises the supply just enough to keep appliances running properly. No excessive increase, no dangerous overload, only the extra push required for stable operation. The wiring method is called a boost configuration. That means the system is not pulling additional electricity from the grid. Instead, it balances the existing supply, so the voltage reaching lights, fans, refrigerators, and wall sockets comes closer to standard levels. Inside the arrangement, the main supply line connects to the primary transformer coil. The boosted output then leaves through the secondary line. The entire design keeps the voltage increase controlled and moderate. Anyone imagining a giant industrial machine can forget that image immediately. The device is smaller than a brick, lighter than a normal toolbox, and if a strong transformer is used, it remains cool during operation. That practicality explains why similar solutions appear in schools and clinics across Indian villages, and even remote African workshops where dependable stabilizers are difficult to rely on. Still, another concern naturally appeared. Would the system handle only lights and fans, or could it support larger appliances, such as washing machines and expensive computers? The retired engineer offered a clear explanation. These homemade boosters work best on smaller circuits, including lighting lines, ceiling fans, and regular plug points. Running a large air conditioner or an oversized refrigerator from a single small booster is not recommended. In those situations, a commercial stabilizer or a custom higher capacity transformer becomes the better option, though the underlying principle remains the same. For typical homes and apartments, separating the load between different circuits is considered safer. After understanding this, the setup was expanded. One booster handled the lighting system while another powered the fan circuit. Both units operated flawlessly. Neither fuse ever tripped. Neither transformer overheated, even after running continuously for 5 or 6 hours during peak evening conditions. The real protection came from the fuses. Anyone attempting a similar setup should install 2 levels of fuse safety, one fuse directly after the plug and another on the output side. These inexpensive glass fuses may cost almost nothing, yet they provide the strongest defense against overloads and accidental short circuits. Safety remained the most important issue because no money-saving solution is worth risking electrical shock or fire. With any transformer-based system, the main dangers are overheating, loose wiring, and short circuits. The first rule is using quality wires instead of thin recycled material. The second is making certain every connection remains tight and fully insulated with no exposed copper visible anywhere. The third is matching the fuse slightly below the transformer's maximum current rating. If a transformer is rated for 6 amps, then a 5 amp fuse should be installed. When assembled properly, the result becomes a legal and safety-focused voltage lifting system for home use. Looking back, the biggest obstacle was mental rather than technical. The fear came from believing the project might be too complicated or that mistakes would ruin everything. That lesson became clear after a cousin decided to copy the original system using an old transformer left from a school project, along with scrap copper wires found around the house. At first, everything worked perfectly. Fans rotated normally, lights stayed bright, everyone assumed the problem was solved permanently, but less than a month later, trouble appeared. The transformer began producing a loud buzzing sound, its casing grew far hotter than the original unit, and one fuse melted completely. The cause turned out to be straightforward but extremely important. Component quality and proper matching. Not every transformer is designed for identical workloads. Using an old, weak, or undersized transformer forces it beyond safe limits. Eventually, the stress becomes impossible to hide. The internal copper windings must remain thick, clean, and undamaged, rather than corroded or partially melted with age. The transformer should always match the highest output demand expected from the circuit. Wire thickness and fuse quality also matter greatly. The cousin discovered this lesson the hard way. Once the weak fuse was replaced and a heavier transformer installed, the entire setup stabilized immediately and stayed cool, even during the worst voltage drops. After several similar minor failures appeared around the neighborhood, monthly inspections became routine. Connections were checked regularly, and whenever someone noticed unusual heat or strange noise, the issue was examined before becoming serious. Most repairs turned out to be simple. Tightening loose screws or replacing a fuse usually solved the problem quickly. The bigger lesson stayed clear. Even the simplest homemade solution still depends on proper quality. If assembled using solid copper wiring, a fresh transformer, insulated sockets, and secure connections, the system could outlast many low-cost imported automatic stabilizers sold online. But there was another side to the experience beyond saving money. Maintaining something built personally created a sense of pride and even enjoyment. Instead of treating every inconvenience as an expensive disaster, people slowly began seeing problems as puzzles they were capable of solving themselves. That change in mindset spread through families, neighbors, and eventually the entire street. Confidence grew quickly. As more people experimented with their own systems, they began sharing small improvements that made the devices even safer and more reliable. Some wrapped electrical tape around every connection to protect against humidity. Others raised the transformer on wooden blocks to avoid water spills in kitchens. A few even positioned small cooling fans beside transformers during hot summer nights whenever extra warmth appeared. And if local electricity eventually became stable and reliable again, the solution remained simple. Unplug the booster and continue normally. There was no complicated shutdown process. No permanent modification. Anyone capable of using a power strip or ordinary plug could handle the setup. After several months, the most noticeable change was not the money saved, but the reduction in stress throughout the neighborhood. No more arguments over spoiled refrigerator food. No more frustration about damaged chargers. No more sleepless, humid nights caused by weak ceiling fans. Eventually, fewer emergency calls started coming from nearby homes because residents themselves had become confident enough to identify and solve small electrical issues independently. The power company never changed. Daily life did. And all of it happened because of one inexpensive and practical homemade solution. Good household economics is not always about giant government programs, expensive technology, or constantly increasing spending whenever problems appear. Sometimes it comes down to resourcefulness, cooperation, and the willingness to learn something useful. This 200 rupee voltage booster may seem small, but it delivered a meaningful answer to ordinary problems most people had simply accepted. The best part was that the solution remained within reach for almost anyone. No magic involved, only the value of learning to do things personally. If low voltage has affected your home, or if you have discovered your own practical solutions, share those experiences with others. Stories, questions, and creative DIY ideas can help someone else facing the same struggle. A single suggestion might end up helping a friend, a family member, or an entire neighborhood searching for relief from powerless nights. Sometimes the smallest transformer can change far more than expected. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.